fixing a consistency issue based on the fact that I just had to drastically restructure my entire talk. Okay. Okay, so I just I
know the feeling. You know, I was fixing my slides until the last minute. So
you know, I was actually on it until I found that I couldn't talk about GGMs. Okay. So if I share my screen, then do I become visible?
Yes.
Okay.
Yeah, I mean, you are already visible to everybody.
Oh, hi everybody.
Yeah, basically, like on the screen, you only see the panelists, right? But basically speakers. But yeah, you are visible to all participants right now.
Okay, cool. Let me just share my screen.
Yeah.
Can people hear me?
So this is good, except that okay, so you're unshared now, right?
Am I not shared?
You are not shared right now. You appeared for a second and then disappeared.
Oh, I tried running it with my PowerPoint running. Let's try this again. Now?
Yeah. No, this
okay,
is good. Yeah.
All
right. So yes, without further ado, Jon will talk about computational complexity of statistical estimation.
So hi everybody, I'm Jon Kelner. I am along with Prasad, one of the people who is in charge of this area of computational complexity of statistical estimation. And so we are very lucky to have a nice, large and exciting team from both schools, which I've put here. And we have a pretty good distribution between both Berkeley and MIT. Some people are even distributed by themselves. Shafi has managed to make it into both. And today what I want to do is just run through kind of the basic goals of the theme and then do some technical stuff. I should give a quick pre-apology, which was that I learned about 30 minutes ago that Encore was speaking about GGMs as well as me. So I have drastically restructured my talk in the last half hour, and we are going to just hope for the best. So I've changed my talk to be a little bit more sums of squares oriented. And yeah, okay. So let me first just say what the high level objective is of our area, and then I'll kind of talk a little bit more about generalities, and then I'll start talking a bit about some specifics. Okay, so the overall high-level objective of this area is to understand the computational and statistical trade-offs involved in statistical estimation. And so this was our kind of go-to blurb, but I want to change it a bit and just phrase it as, what should complexity theory look like for data science and statistics? So, and I'm going to give a little warning here, which was I'm about to caricature both statistics and computational complexity. And I figure as long as I, as a TCS person, caricature computational complexity as aggressively as statistics, then it's probably okay. Okay, so the short version of a motivation for this theme of our of VODC is just that classical statistics largely focus on sample complexity and not computation. And I guess I will make myself safe in this statement by, if there's anything that does involve computation, just officially declaring it not classical. But broadly speaking, you know, the main results are what you could do from an information theoretic standpoint. What can you hope to do if you have infinite computation time? And lately, what's been becoming increasingly clear is that there's a really substantial trade-off involved. And that if you look at what you can do with finite computational resources, that definitely is not always the same as what you can do with infinite computational resources if you just look at the information theoretic complexity. And more broadly, there's been kind of an emerging structure of trade-offs between the quantity, quality, and just of the data that you have and the computational resources you're willing to devote, and how these relate to what statistical problems you can solve and how well you can solve them. And so I would put the goal of this research theme as saying that it will be to develop frameworks, algorithms, and intractability results to explore this sort of new class of trade-offs. And I think, you know, in an ideal world, what we would end up with is something that looks like what complexity theory looks like now, namely something where we have an ability to really precisely ask the question of what is hard or easy, find the right ways to get the primitives to which one can reduce in order to get decent computational hardness results, and then get algorithms that come as close as possible to matching them. Okay, so My first generality before I get to some content on this was that classical computational complexity is really not very well suited to data science questions. And this was my hopefully aggressive enough criticism of complexity theory that people will forgive me for saying that statisticians don't know about computers. And so why this is reasonable is that, reductions to NP-hard problems, I guess, are the bread and butter of a first course in complexity. And anything in that vicinity tends to, they're very hard to come by when looking at data science applications. And in particular, the reason is that usually the questions that you want don't really care about real instances, but you care about instances that correspond to reasonable probability distributions. And typically when you go through a reduction process, you end up with some very contrived or complicated distribution. And it tends to be very hard to get these to be well adapted to problems where you actually want to solve from reasonable distributions or say something reasonable about problems you actually encounter. And there's actually even kind of a stronger statement, which is that there are complexity theoretic results that say that you can't use complexity theory, in that there are a bunch of results that say that under certain computational true assumptions, you should not be able to get NP hardness reductions for a lot of the sort of interesting classical problems that you'd want to solve in a statistical estimation kind of context. And so what I want to talk a little bit about are just some possible other directions. And then I'll, rather than trying to survey all of them, I'll just give some background on one of them, the one that remains after Encore's talk. And then kind of conclude by saying a few words about the general directions one can go. And so, the question is, what can we do if we're not going to say things are NP hard, but we want to say things are hard? And one answer is just reduce to something else. And that actually has been surprisingly profitable. I'll say more about that shortly. The other answer is that you could imagine looking for unconditional lower bounds in weaker models of computation. And I'll also say a little bit more about that. So, the first one is you're going to, instead of looking for NP hardness, you'll try to find a new notion of hardness. The second one is try to get lower bounds in some model that is not, that is not all Turing machines. And then the other things that we'll focus on in this theme that I'm not going to talk much about today are going to be insights from statistical physics and lower and upper bounds against specific classes of algorithms. And so there's been a lot of great work that's been done by a lot of the people on that previous slide in this direction, but just for time constraints, I'm going to shy away from it. Okay, and then of course, there's the very popular machine learning approach these days, which is that you'll just assert that neural networks solve all of your problems for all parameter regimes, and thus the complexity is not a problem. That one I'll also not talk about much today, but hopefully nobody else will either. Okay, so the broad goal in this research team is going to be look for algorithms and lower bounds. And one of the things that's come out is a very popular way to do this. And it's something that's been very useful, both from some things I've worked on, but also things that other people who are in this group of this research team have worked on, has been the planted cleat problem. And so I just wanted to, so we have a little bit of context, talk a little bit about it, because it actually has been playing a substantial role in the complexity theory to come. In fact, something that's been developed quite a bit by Philippe and Guy, so Philippe Rigolet and Guy Bressler, among others, has been the possibility of it giving us one of the basic reductions that we can use, that we can develop planted clique hardness as a stand-in for NP completeness. Okay, so let me briefly just tell you what the planted clique problem is. I'm not sure how many of you have seen it before, so I'll just run through it a little quickly. But the question is the following. So the idea here is, and so why I'm doing this before I tell you what it is that it's going to be two reasons. One is that it is a problem that people think we can't do well. And so it will illustrate, and it turns out this has emerged as a really good example of something to reduce to. The other is I'll talk a little bit about a result that I and a couple co-authors, including Encore, have come up with that was the start of a bunch of work on unconditional lower bounds for classes of algorithms that potentially could be ones you could actually analyze in a statistical setting. Okay, so planted clique. So the setup is as follows. The idea is you're going to start with a random graph. And so by a random graph, I mean an Erdos-Renyi random graph, which I write as G n a half. And if you haven't seen this before, it just means every edge is in the graph with probability a half. So you randomly and independently choose whether to include every edge. And now, if you look at such a graph, the biggest cliques in it, it's a very classical result. The biggest cliques in it will be of size of log n. And that was one of the first reasons why first results in the theory of Erdős-Rényi graphs. So you should think there's a log n-ish sized clique in their graph and nothing bigger. And then what you're going to do is you're going to, on top of it, you're just going to throw in a clique with a whole on some smaller set of vertices. So you'll pick some number omega that we'll talk about what it should be in a little bit. And you just add that as a clique to your graph. So you take your original graph and you union it. Some size omega. And now you should think like an interesting value for omega should be bigger than the original clique, the biggest clique in your graph itself. So think of omega as being, at least a large constant time, at least a constant bigger than 2, say, times log n. And then the question is to find the clique. So if the clique is bigger than you would, with high probability, expect to find in a random graph, then so it's with very high probability true that you won't find substantially larger than, say 2 log n clique in the random graph. So if you found one, it should have something to do with your planted clique. And so the goal here is to find it. And from an information standpoint, this problem is super easy. And in fact, all you do is you just try every subset. But the question here is, what is the first question, kind of the one that started this process was, when can you actually do this? What are the omegas that actually make this a solvable problem? And so let me briefly say the sort of what was known about it, and then I'll talk a little bit about where we are on it now and what it's useful for. So there is a very easy algorithm that is quasi-polynomial time. So if I gave you any omega greater than c log n for c bigger than 2, there's a nice easy way to find a planted clique. You just try every subset of size omega, and that if you find a clique that's much bigger than you should have in your graph, it has to have a substantial overlap with your clique, and then you just do a little bit of cleanup. So that's the easy answer. And the easy answer is in n to the log n, you can find any sufficiently large clique. There's then a very easy polynomial time algorithm for a much bigger value of omega. Namely, if omega is root n times log n times a constant, there's actually a very simple polynomial time algorithm to find the planted clique. And if you haven't seen this before, maybe think for 3 seconds of how to do it before I tell you the answer. Okay, so if you planted a clique that was substantially bigger than, that was c root log n times n, so that will make the degree of a vertex bigger than you'd expect to find in a random graph. So a random vertex should be of degree, well, it should have neighbors with half of the other vertices plus something that's like root n times a constant. So if you got root n log n times a sufficiently large constant bigger than that, then you shouldn't see that unless the vertex is in the clique. And so that is the easy algorithm. And so right now I've given you 2 easy algorithms, and there's a giant gap between what's polytime and what's not polytime. And then there's one step more that you can do, which is that you can get rid of the root log n. Oops. You can get rid of the root log n using a spectral method. And so this is kind of the start of the more modern algorithms for the problem. It turns out that you actually have to do something a bit smarter in order to go from root n log n to root n. And there's a result by Alon, Krivelovich, and Sudakov from '98 that says that there's actually a polytime algorithm for finding cliques of size c root n or bigger. So we've shaved off that root log n. And there, the algorithm is a spectral one. So you basically, instead of looking for high degree things, you're going to look for big eigenvalues and corresponding eigenvectors and go from there. Okay, so that is the planted clique problem. And why I bring it up is for 2 reasons. So the first one is that it's actually emerged as a hardness assumption. And so this started with Philippe and Berthier's work on PCA, and they actually managed to show that, so planted clique is a statistical problem, which makes it a plausible candidate for reductions. So, the problem with why you shouldn't try to reduce to 3-sat is that that's an absolute kind of problem. It's not there's no randomness in the description of the question. It's hard to imagine getting a natural distribution to come to it. Now, the reason that planted clique has emerged as a plausible, hard problem to be studied here is that it actually is one that encodes a distributional assumption in a natural way, and is still one that we don't know how to do better than still one where we have a substantial gap between what is information theoretically and computationally tractable. And so people actually have tried a bit to do better than the root n. And as of now, there is no better algorithm than root n for the clique you can find in poly. So, pattern of complexity theory, when one can't solve a problem or prove it's impossible, you just name it and call it planted clique hardness. And so and it's turned out that this has been a really good building block for a lot of computational hardness results in this in these sorts of settings. And so Philippe and his collaborators have shown some of these and started this area where they showed that you actually could show that certain conjectured computational statistical gaps for the planted for PCA actually come from the planted clique conjecture. So that is if you the base conjecture here is going to be that this problem is hard, and you can actually show that this implies other problems to be hard as well. And since then, this has taken off. So there's been a whole bunch of reductions to show statistical and computational trade-offs. And recently, one of the theme directions has been understanding whether this is the right problem and how far you can get with it. Recently, there's been huge amounts of progress made by Guy Bressler and his collaborators in terms of showing how well this does as a good basic assumption. Okay, so that was planted clique. And due to my slight curveball on my talk topic, I am now going to talk a little bit about how not to solve the problem. And so the natural question you'll ask is it actually hard? And I've always thought that, computational complexity theorists were such pessimists, and that, root n just like there's this giant log n to root n gap. And coming into this as someone with an algorithmic kind of bent, I always felt like the goal should be to do better. And so there's a very natural candidate for a class of algorithms that could hopefully do better on solving planted clique. And it's called the sums of squares hierarchy, or the Lasserre hierarchy. And what I'm going to do with the rest of the talk is first I'll tell you the end result of where we're going with this, and then I'll tell you what the hierarchy actually is. And then I'll say a little bit about how it ties in to the general goals of our theme. Okay, and so the question I want to ask is it actually hard? And what I'll describe for you on the next slides is a way of creating a hierarchy of successively slower but more powerful algorithms. And so what we'll see in a second is that you'll have a parameter t, and if for every value t, you'll get a stronger algorithm with a running time that grows like n to the o of t. And so if you could solve this problem for t equal to some number that was sufficiently small, that was say a large constant, you could then get a polytime algorithm for the problem. And I'll say a little bit about why, but the reason that this is a plausible conjecture is that the spectral algorithm can very much be interpreted as the t equals 2 version of this system. And so I kind of had hoped the answer was that this was impossible, that this was possible, that you could actually, with even t equals 4, plausibly do better. There was a sequence of papers that showed, well, there was a paper that conjectured to produce an integrality gap for the entire, all hierarchies up to like a root log n degree. And it turned out to have a subtle bug that made it not a true proof. And what made me really optimistic that we could solve planted clique was that actually the algorithms I'm about to describe could, that the algorithms that I actually describe they actually at least break the integrality gap instance that was previously known. And so the somewhat disappointing result from an algorithmic standpoint, but good building block from a complexity one, is that actually the sums of squares hierarchy I'll describe for you in a second has an absolute unconditional lower bound on planted clique problems. And so the result is that that for anything less than n to the 1/2, so n minus any constant, or even n minus c root d over log n, you just can't do it. There's an integrality gap for the sums of square hierarchy. And in fact, for any sublogarithmic degree of the hierarchy, you just can't find any clique of size substantially smaller than root n. And so why I mention this is that now between these two, this starts to give a hope of proving both conditional lower bounds for computational complexity problems and unconditional ones against this class of algorithms that I'll motivate for you now. Okay, so let me tell you about the sums of squares hierarchy, and then, okay, so this is something that's been turning out both on a positive and negative side to be a very powerful technique for understanding problems in statistical estimation. It's got both the best best algorithms for a bunch of problems, as well as just being a hardness result. And it was introduced in a couple different forms. And I'm going to introduce it in one that's not the way that any of these forms introduced it. It's, I guess, closest to the way Lasserre had, but not really. And so let me describe the goal as follows. So the goal is that we want to solve some optimization problem. In the problem of planted clique, we're going to think our goal is to find the hidden clique. So we'll phrase this as just find a large clique in our graph. And the sums of squares hierarchy, what it does is it asks us to try to find something that's going to pretend to be the moments of a random variable supported on solutions. And so let me say a few words about why that's reasonable. So the idea here is we're trying to find the biggest clique in a graph. That is not a convex problem. That is not a polynomially time solvable problem in general. And so what we're going to do is we're going to try to frame this in a convex way. And the way we'll do that is we'll say, okay, how do you ask a convex problem? Well, if we want to ask for a convex set to look for, then we can't look for one solution because it's possible there could be more than one. And then there's no way you can, as a convex sort of setup, know which one to pick. And so instead, what we're going to do is we're going to look for a probability distribution over all solutions to our problem. So that at least is a convex thing, because we're looking over all probability distributions, but it's a grossly unsolvable one. It's harder than our original problem, if I want to find, or at least as hard. And so instead, we're going to, our relaxation here is that we're just going to, instead of trying to find the probability distribution, we're just going to try to find things that look like they could be its moments. And so this is the way I want to frame the sums of squares hierarchy. This is really the Lasserre hierarchy. And what it says is you're going to look for an operator that inputs polynomials of degree less than or equal to d and spits out numbers. And those numbers are going to presume to be the expected values of the polynomials that are given as inputs. And we'll call this a pseudo expectation. And so what I'm going to do to define the hierarchy is I'm just going to define the rules that these pseudo expectations should obey. And just in case you've seen things in other settings and haven't seen this yet, note that classical semi-definite program relaxations are going to directly correspond to this at degree 2. Okay, so here are the constraints that we're going to have. What are they? So we want to define expected value, like we want to try to find something that looks like it could be the expected value of polynomials. And what do we know about this? So first of all, we know it's linear. We know that the expected value of 1 is 1. And then there's the real constraint that carries the strength of the hierarchy. This is kind of the main one that actually really is what gives you computational leverage. You want to show that for any polynomial at all, note that if I were to square a polynomial over the reals, I get a non-negative number for any value that I plug in, because squares are non-negative. And so all we're going to do is we're going to assert that the expected square of any polynomial is greater than or equal to 0. And now if you think about that, if what we're going to try to do is make a big list of moments of our random variables, so we'll look at the expected value of every monomial, this now gives us a whole bunch of constraints. It says any sum of these things that actually corresponds to the square of a degree less than or equal to d over 2 polynomial has to have a non-negative expected value. Okay, and so this is the general hierarchy. I now want to throw in some more that will be tailored to the planted clique problem, and then, and what will those be? So in the planted clique problem, we're looking for a 0-1 solution. And so we know that the x's, the variables that we're trying to find, well, how should we actually encode our problem in this form? We should encode it as saying, let's try to make a vector that's got a 1 in every component on the clique and a 0 outside of it. And so for that, we can then just that gives us the constraint that x squared equals x for every one of our variables. And so we have as the assumption when encoding the fact that our solution should be 0, 1, we'll throw in this constraint. It will say that for any polynomial, if x squared equals x, then x squared times p should equal x times p. And note that x squared equals x is precisely a quadratic that encodes that you're 0, 1. Okay, so the other constraint we're going to do is we're going to look for a big clique. So we'll require that we have we're trying to find the moments of a probability distribution over a clique of size omega. And so over cliques of size omega, so we'll encode that the expected size of our clique is omega. Now, if we're putting an indicator function for the clique, that just means the expected sum of the x of i's is omega. And then edge. And we don't take any xi and xj when there isn't an edge. Okay, and so that is it. That is the sums of squares hierarchy. It turns out that you can actually solve it. So it turns out that if you have, first of all, this is a way of encoding our clique problem. If you imagined removing the little tildes from all of our e's, and I were to just say for you, find a probability distribution whose expected values for polynomials meet these constraints, this would exactly encode looking for a probability distribution over cliques of size omega. And so that would be great. We would have the answer. And so the tilde is just the relaxation where we're only going to require that we obey these constraints on expected values of polynomials rather than being an actual distribution. And it turns out that there is an n to the O of d time for finding such operators called the degree d sums of squares algorithm. So since I'm running a little short on time, let me say a couple more words about how this fits into everything. So now, why is this relevant to getting data science's complexity in place? Okay, so first of all, this is a very plausible algorithm for solving a lot of problems. I initially thought sums of squares would solve planted clique, and it doesn't. I was very upset by the result. But it turns out that this techniques in it that we use to do this were actually very well suited to proving hardness results for distributional problems with sort of distributional inputs. Some things like planted clique, where you're trying to find some sort of structure in a sea of randomness. And the techniques in this work actually have led to a bunch of different directions for understanding how to construct lower bounds for these relaxations for a bunch of these problems. On the flip side, it hopefully provides some grounding for understanding both how we can get other problems with unconditional lower bounds, and I don't know, maybe it also will tell us a better way to solve the problem. I'll remain optimistic as an algorithmist. Okay, so I think I am out of time. Thanks everybody. And if there's any questions, just let me know.
Cool. Thank you, Jon. Thank you, Jon. So let's see. I think we have slightly less than 1 minute for a question. So if there is any question, please type them in the Q&A. And in the meantime, Bin, are you there?
Yes, I'm here.
Okay. Yeah. In the meantime, I guess you can start setting up your slides.
Do I have the right to share the screen?
Oh, sorry. Let me now I think you do.
Not until
Okay.
Jon.
Thanks, Jon.
Sorry.
No problem. Okay, so I don't see any questions. So thanks, Jon, again.